Okay, I'm recording this now. So I'll post this recording on the Moodle page, okay, or at least a link on the Moodle page if I have trouble uploading it there. So here, through what potential difference would an electron need to be accelerated for it to achieve a speed that's 4.3% the speed of light if starting from rest? Okay, so potential difference, just real quick here, let me see if I can draw on this a little bit. When they ask for potential difference, okay, notice what the answer is. The answer is going to be in volts. Okay, potential difference is a way of saying solve for voltage. I know it sounds a little bit like, oh, we're solving for potential energy. Yeah, that's where it's a little tricky in this unit, is that it's not potential energy we're solving for. We're solving for potential difference or voltage. Okay, so let me go here and let me show you what I would do with a problem like this. I guess my starting point here is I'm going to say my potential difference or voltage difference equals my change in potential energy divided by charge. Okay, on that last slide of the slideshow, I mentioned that this is the equation I would use in problem number 1. Okay, so let me take this and go up here. Say my starting point on a problem like this, we're trying to solve for we're trying to figure out what would be needed to solve for a final velocity. It's going to go through a potential difference. It's going to go through a change in potential energy here. Okay, so my thought is, well, let's think conservation of energy. U1 plus K1 equals U2 plus K2, potential energy. Now, let's acknowledge, first of all, it starts from rest. They mentioned that right in here. Okay, so we can get rid of that. And now let me do this. Before I plug in any numbers, let me rewrite U1 minus U2. U1 minus U2 equals K2. I just did an algebra step. I took this to the other side of the equation. Okay, well, let's call U1 minus U2, let's call that delta U equals kinetic energy at position 2. Okay, why would I do that? Because notice when I solve for this change in potential, that can go right in here, divided by the charge of this particle, should give us a final answer. Okay, so if we could just do this, 1/2 mass times velocity squared at position 2, that's going to allow us to solve for our change in potential energy. Now here's the one trick, is this value here. Let me put a great big parenthesis here. What they said about that is that they want to get to a speed 4.3% of the speed of light. Okay, so what I want to plug in here is 4.3%, written like this. Oops, almost did that wrong. There's 0.43% of the speed of light. I think, what do they say, 2.998. Okay, all of that is inside the blue parentheses so that I remember to square that entire speed. I'm not just squaring the speed of light. Okay, I'm squaring 4.3% of the speed of light. Okay, so that's the one trick for this. Now, again, what I've got in parentheses is not the final answer. You do need to plug in 1/2 of the mass. What is this particle? Of an electron. Okay, it did say electron, so make sure you're putting in the mass of an electron there. All right, anyways, so that's the thought process with this problem. Okay, and again, I'm not quite done there. I think it's important, though, that we do recognize that that change in potential energy we just solved for can now get plugged into our voltage difference equals change in potential over charge. Okay, that's how I'd go about number 1. Okay, now I'm hoping, I saw some people have gotten a start, but not too many. I'm hoping that helps you out there. All right. Okay, I'm gonna leave that one as it is, let you finish that up. I'd like to go on to another slide here. Okay, I've got assignment, question 4, 5, and 6 all together here. Those all go together. Okay, part 1 of 3. Okay, so the next 3 questions all go together on this. Okay. Anyways, so now at this point, oh boy. Sorry, I don't know if anybody can hear the dogs barking upstairs, but it's a real distraction. My apologies. You've got a proton. Okay, it gets released from rest in a uniform electric field. Okay, released from rest is going to be an important piece of information. In this uniform electric field, okay, there's an equation that shows up that we haven't really talked about in a long, long time. Okay, what I want to point out is that we can use this electric field between parallel plates. Okay, and we can say that's actually equal to the voltage between those parallel plates, voltage difference, divided by the distance separating them. Okay, now it's been a long time since we've talked about parallel plates, but you've got a positive plate that's attached to like positive terminal of a battery. You've got negative plate that's attached to the negative terminal of a battery. Okay, that's what's giving these any charge. Okay, turns out that that voltage difference that these are attached to, that's the voltage difference on these plates. Okay, if we know the distance between these, we're in shape. We're in good shape. Okay, let me get rid of this. Okay, so on this problem now, again, what this comes down to is taking a look at the voltage that we know, 60,000 volts per 60,000 volts per meter. Pardon me, that's the electric field. Taking this distance that we know, the distance separating those plates, and solving for the one unknown. Okay, so the known values here, excuse me, the known values here are the electric field in volts per meter and the distance in meters. Okay, we can just solve for voltage here. Okay, so I don't know, let's do this. Let's, let me take this, multiply both sides by that distance. Okay, and we should get that voltage difference. Okay, if you want to grab your calculator and do this one real quick, this one just comes down to two numbers typed in on your calculator. 0.4 meters, 60,000 volts per meter. Okay, even those units kind of help. Volts per meter times meters, that's going to give you voltage. Okay, that's going to tell you what the voltage difference is between these two plates here. Okay, and that should come out to our 24,000 volt difference. Now, they did give you a negative value there. Okay, that negative out front is just implying that it started, this positive charge started close to the positive plate, ended up close to the negative plate. Just like in circuits, you've got a voltage drop. A voltage difference is showing up from a place where it's got high potential energy to a place where it's got low potential energy. It's got a voltage drop going from high to low. Okay, so that's what that negative is for. All right, so let me scroll down a little bit here. Okay, if we look now at the next question, it says find the change in potential energy of the proton for this displacement. I want to point out the wording that they use, change in potential energy. Sometimes it's tough to tell. Are we looking for, are they talking about voltage or are they actually talking about energy? When they use the word energy, okay, we're talking about U. Okay, delta U is what we're going to solve for here. Okay, so that's going to be kind of important that we take a look at. For this problem here, there we go. For this problem here, I think what we want to look at is that our voltage difference is equal to our change in potential energy divided by the test charge. And again, that test charge that's moving through here is a proton. So we know the charge of a proton is just the elementary charge. Okay, the change in potential energy is what we're looking to solve for. Here, I want to point this out. What do we do here? The voltage we just solved for in part one, okay, is going to be what goes into this equation. Okay, so our last step here, let's just, oops, oh, well, I might as well. I just wanted to take that Q, multiply both sides by Q. I'm left to right. Okay, multiply both sides by Q, and we should be able to solve for that change in potential energy. Okay, charge, just keep in mind, is the charge of a proton. Okay, and that one, I forgot they didn't tell us that number, so I want to just remind you, charge of a proton is the same as the charge of an electron, which is 1.6 times 10 to the negative 19th 19th coulombs. Okay. Anyways, if you double check that, it's basically this number here multiplied by the charge of our proton. That should give you an answer right down at the bottom of my screen right now. Well, I got some lag time here. There we go. Down at the bottom of my screen, you should get something that looks like this. Okay. All right, let me continue on because I know I'm starting to take way too long here. We're coming up on 40 minutes. The last question here now, apply the principles of energy conservation to find the speed of the proton after it's moved that distance. Okay, if it started from rest, it simplifies things a little bit. Okay, let me do this in another color here. Or try orange. All right, basically what they're looking for us to do. Here, let me skip a step just because I'm going too long here. Our change in potential energy should equal our change in kinetic energy. If I did it the long way, I'd put in U1 plus K1 equals U2 plus K2. 2 algebra steps later, I've got U1 minus U2 equals K2 minus K1. Our change in is what we're looking at here. All right, so at this point, we just found our change in potential energy. Okay, is this value here. So whatever we just solved for is going to go in for our change in potential energy. We can set that equal to 1/2 mass times velocity squared. Okay, that velocity is at position 2. That's what we're looking for right in here. Okay, so solve for V2. Okay, we can set that equal to our change in potential energy we just solved for. Anyway, so we're right there. What do we need to know for this? We do need to know what the mass of our proton is. Okay, but they gave us that value. It's up here somewhere. Here it is. The mass of a proton, they told us. Okay, 1.67 times 10 to the negative 27th kilograms. Everything is there that we need. Okay, potential energy, mass. Let's solve for V squared. Or excuse me, just solve for V. And we should end up getting an answer that looks something like this. Okay. If you want to screenshot that, you can. But like I said, I'm recording this. I'll post this recording. As long as I don't have any issues uploading it, I should be able to post that recording. Okay. Tell you what, there's one more I'd like to go through. So I'm going really quickly here. I had someone actually email me about this question. This is a really good question, I feel like. And there's one key concept that we haven't said out loud yet that I want to make sure we say that you really need for this problem. Now, we've done problems like this before. It looks like we're dealing with, okay, we want to solve for the voltage at point P. Okay, find the electric potential. Well, that's just a fancy way of saying find the voltage, okay, at point P. All right, that's caused by these 3 charges. Well, we did that when we talked about electric field. What's the electric field right here? Well, we would take KQ over R squared, KQ over R squared, KQ over R squared. It's a little bit simpler than that because we don't have to deal with the R squared version. And there's one more thing that simplifies it also. But let me just write this out first, is that voltage due to each one of these point charges here is going to equal K times that point charge divided by R. Careful it's not divided by R squared. Simplifies it a little bit, okay? So just divide by R. And then what we do with this, okay, is we can maybe take this charged particle here that's positive, K, Q, divided by this distance squared. Okay, all that's given. And let me highlight this distance, it's right here. All right, we've also got this K, Q, divided by distance squared. Here's the one tricky thing about this distance is that we've got a diagonal distance we're gonna have to figure out. They didn't tell us that, but you can do geometry pretty well there, no problems. And then we've got one more here. You've got this KQ over distance squared. That distance is given right here. Okay, so just match up your Q's and your R's. And what this comes down to is just taking a sum. Okay, to find out the total voltage is going to equal the sum of our voltage 1 plus voltage 2 plus, see that? Voltage, oops, darn it, plus voltage 3. Oops. And maybe I should have done those in highlighter colors, okay? What did I do with voltage 1? Voltage 1 was the one that I did in blue, okay? I botched that. Sorry, guys. Still getting the hang of this thing. Voltage 1 is the one that I did in blue. Voltage 2 is the one I did in green. Okay. Voltage 3, the negative one, is the one I did in yellow. Because it's negative, we're going to use a negative voltage there. All right. And here's the nice thing about it is you might look at this and remember, oh, when we did electric field, we had to do like Pythagorean theorem. We had to find all the X components and Y components. The nice thing with voltage, you don't need to do any of that, okay? Because voltage has to do with potential energy. Remember the direction of potential energy. No direction. Oh, that says no direction, okay? Voltage, no direction. Okay, you don't have to find components for voltage. You don't have to find Pythagorean theorem for voltage. The one Pythagorean theorem you might need in this problem is just to figure out the distance that separates this charge from point P. Okay, the nice thing with this is we're just adding up whatever that voltage is plus that voltage minus the third voltage. You're just adding numbers, adding and subtracting numbers with no direction to them. It's the same as adding 5 plus 3 minus 2 or whatever the answers are. No direction is necessary. So that's actually a little bit of an easier problem than some of the others that we've done in past that look like this. But we needed to be aware of that. Okay. And let me do one more thing because I don't have the answer on here. I've got to write it down for you. The answer that I got for this, our net voltage, just so you can check your work with my numbers if you like, I got 3.13 times 10 to the 5th. And that's in volts, okay? Okay, 3.13 times 10 to the 5th volts. Anyways, so I think that's the last one that I wanted to go over today because I'm out of time. I've held you here for almost 50 minutes. So here's what I'll do. I'm going to close down this screen. Okay, I'm going to stop the recording also. And I can take questions for just a minute in the classroom. If you want to see this again, just go to the recording. I'll try to get that uploaded right when we're done here. Okay, so let me see here. I need to